Okay, I think we can get started.
Sure.
So thanks everyone for coming. Today we have Ravi Shroff from New York University, and he is a fellow statistician. So I'm really proud to present. You might be the first statistician to talk in this series.
Oh, cool. Okay.
Hopefully we'll have more join us in the future. And so when I was putting together the schedule, I was looking for fairness, transparency, accountability in the data science research. And another important area is interpretability. So I started Googling and then found Ravi in my Google search, and then his research on interpretable statistical models looks really interesting to me. So that's why I'm very glad that we have him talking today. Thank you.
Yeah, thank you very much. So thanks so much for the invitation to be here. It's a real pleasure. So just to introduce myself briefly, I'm an assistant professor of applied statistics in NYU Steinhardt School and also urban informatics in NYU Center for Urban Science and Progress. So today I'm going to talk to you. I'll introduce my research interests, and then I'll talk about simple rules for making decisions. And I'll give two applications, both to the criminal justice context. One to investigatory stops by police officers, and the second to pretrial detention decisions made by judges. So I think we have a Q&A period at the end, but feel free to interrupt me if you have any kind of clarifying questions or anything. I'd be happy to take them. So just to tell you a little bit about my research interests, broadly speaking, I care about social issues, usually handled by city and state agencies that affect vulnerable populations. And I'm interested in understanding these issues by using and developing new statistical and computational methods. I'm particularly interested in implementation. And so what I mean by that is a focus on creating and evaluating tools that can be used by people with limited statistical expertise. And I'm also interested in how ethical and legal concerns interact with the technical problems that are involved in creating interpretable rules for making decisions. So I collaborate with a variety of city, state, and nonprofit institutions, a lot of them here in New York, and some of these involve ongoing collaborations. So problems in these areas are hard for a number of reasons. So the first is that there are often complicated ethical issues at play, so tensions between public safety and individual rights, racial discrimination, fairness versus effectiveness. Second, to really try and address these problems properly, you often have to have detailed domain knowledge. Data generating processes are often pretty intricate. And in practice, what this means is that I usually work in collaboration with domain experts. Data that you work with on these problems is often observational data, and it's usually or often highly sensitive and poor quality. So this affects the range of solutions that I try and apply. And then also when working in collaboration with city and state agencies, there are often external pressures that shape the kinds of solutions that you need. There's requests from the mayor's office, for example. So despite all these difficulties, we have to come up with solutions that acknowledge these trade-offs between ethical and legal concerns without sacrificing technical rigor. So in this talk, I'm going to describe a methodology for addressing two concrete problems that involve many of these issues. Okay, so simple rules. What are simple rules? So to motivate the rest of my talk, I'll start with the following observation, which is when making decisions, experts often rely on experience and intuition, even though a lot of evidence, a lot of research shows that intuitive judgments are generally outperformed by those based on statistical models. And so when I say experts, I want you to think of, say, doctors diagnosing patients, judges making decisions about whom to detain or whom to release, managers deciding who to hire. So if this is true, this raises this question, which is why do practitioners avoid using statistical models? And one answer is that statistics is hard, and it's difficult to create usable models, it's difficult to understand them, and it's difficult to apply them. So what I would like to ask is, what if there were statistical models that could be used to inform decision-making that are fast, frugal, and clear. And so what I mean by fast is that these are rules that can be applied mentally without the use of a computing device. They're frugal in that they're based on limited amount of information. And they're clear in that the grounds for decision-making are clearly exposed. And so what are the benefits? Well, rules that can be applied mentally may be more likely to be adopted and used consistently by practitioners in the field. And transparency is important because it engenders trust and it can facilitate auditing. That's particularly important. And trust is important, particularly relevant in the public sector. So I should also mention that transparency may even be a legal requirement. There's this general data protection regulation in effect, going into effect in the EU. And some have interpreted some of the clauses in there to actually give a legal requirement for transparency in algorithmic decisions.
Just trying to move this a little bit lower.
Oh yeah,
anyway,
sure.
Doesn't matter.
Hopefully there's not too much going on in the lower right part of the screen. So what do I mean by simple rules? So here's an obviously contrived example. And I'm going to focus on these integer weighted checklists. So here's a contrived example for, let's say, a doctor diagnosing a patient with a disease. So there's 3 items on this checklist. They're all binary. Does a patient have high blood pressure? Yes or no. Does a patient have a rapid heart rate? Yes or no. Does a patient have elevated temperature? And maybe you have a patient comes in who has high blood pressure and an elevated temperature, so they would get a score of 1 for the high blood pressure, 3 for the elevated temperature, their total score would be 4, and you compare that to some threshold determined ahead of time, let's say 3, and if the total is bigger than 3, the patient would be diagnosed with an illness. If the total is less than 3, the rule would suggest that the patient doesn't have the illness. So a few things to highlight here, right, is this rule, it uses small integer weights, small integer scores. It just relies on a few factors, and this whole procedure could be carried out in your head. So I'm going to discuss the construction and evaluation of these simple rules using 2 examples from criminal justice. And these examples are going to, in particular, highlight a simple strategy for creating these simple rules. And in both of these examples, so the punchline is at the bottom of this slide, which is that in both of these examples, as well as in other contexts, we'll see that these super simple, kind of surprisingly simple rules perform comparably to much more complicated state-of-the-art machine learning methods. Okay, so let's go to the first application, which is to stop and frisk in New York City. So just an overview, stop and frisk is this policy where police officers can briefly detain an individual if they have so-called reasonable and articulable suspicion that crime is afoot, and they can conduct a pat-down or a frisk if they suspect additionally that the individual is armed and dangerous. So this standard of reasonable and articulable suspicion was codified in a 1968 Supreme Court case, Terry versus Ohio, and in fact, these stops are sometimes called Terry stops. So to give you a bit of history, between 2006 and 2012, NYPD officers made over 4 million stops, and just for reference, New York City's population is over 8 million, a little over 8 million. And also about 80% of individuals who were stopped were Black and Hispanic, whereas Black and Hispanic individuals make up about 50% of New York City's population. So in 2013, a federal district judge ruled that stop and frisk in New York City specifically was unconstitutional. And these constitutional issues revolved around 2 aspects. So the first was Fourth Amendment issues, namely that stops were conducted without reasonable and articulable suspicion. And then 14th Amendment issues. So the stop policy was not conducted in a race-neutral manner. Now I should point out that proponents of stop and frisk say that if you heavily enforce minor crime, then you sort of indirectly reduce more serious crime in line with the broken windows theory of policing. So my collaborators and I, when we examined stop and frisk, we created a statistical framework to try and understand these issues of constitutionality. But this same framework also suggested a way to potentially make better stops, and that's what I'd like to talk about. So I'd like to start with this question of what makes a stop effective? And this is a tricky question, and it really depends on who you ask. But there's a few things that I'd like to highlight. So first of all, 90% of stops, around 90% of stops resulted in no further enforcement action, meaning that no arrest was made and no summons was issued. Next, the stated goal of stop and frisk was to get weapons and drugs off the street. Now, there's also issues of deterrence effects, although I should point out that it's unconstitutional to stop people based on deterrence alone. There are issues related to community trust and erosion of trust in the police. There's, of course, the individual burdens on the person who is stopped. So I'd like to rephrase this question as, can we use statistics and machine learning to make better stops? Where better here means stops that are more likely to result in an outcome of interest. Or maybe I'll even rephrase that again and say, can we use statistics or machine learning to make fewer unproductive stops, where an unproductive stop is a stop which is unlikely, let's say, to result in an outcome of interest. So what we looked at was 750,000 stops which were predicated on criminal possession of a weapon. So an officer is supposed to, in theory, articulate the reason why the stop is being conducted ahead of time. So these are stops where the officer suspected that an individual had a weapon. So we looked at 750,000 of these stops between 2008 and 2012, and we optimized for weapon recovery. So just to give you an idea of scale, in these 750,000 stops, they comprise about 25% of all stops that were made in this time period. There were, I think, something like 27,000 weapons found. So that's about 3.5% of the time in these CPW stops a weapon was found. And most of the time they were knives or other kinds of cutting instruments. And only about 10% of the weapons found were actually guns. And so why do we optimize for weapon recovery? Why do we focus on weapon recovery as opposed to, say, whether or not an arrest was made as our outcome? And there's a few reasons. So the first is that there's arguably less officer discretion involved in whether or not a stop uncovers a weapon as opposed to whether or not an arrest is made. And secondly, there's a direct ex post justification for whether or not the stop was successful, right? I mean, you could think about, suppose a stop is predicated on criminal possession of a weapon, an officer stops somebody, they find drugs, let's say, and they make an arrest. Was that stop really a stop we would call successful? So that's why we focus on these CPW stops. And I should mention this is joint work with Sharad Goyal and Justin Rao, who's obscured behind the box right there. So what's the data that we use? Well, in New York, after a stop is made, this form called the UF-250 form is filled out by an officer and it's entered into an electronic database. And this data is now made annually public on the NYPD, on a website, I think maybe the NYPD's website or website owned by the city. And as you can see, it's pretty detailed. There's a lot of information about the individual and the circumstances of the stop. So let's take a look at a few more aspects of this data in detail.
Yeah, that's a better location.
Okay, so just to zoom in on a few things on the stop, we can see that the data includes the time of the stop, location of the stop, whether it occurred inside or outside, whether it was in public transit or public housing. Importantly, there's these 10 so-called primary circumstances which led to the stop. So these could be things like carrying objects in plain view used in commission of a crime. For example, Slim Jim or pry bar, or suspicious bulge or object, or furtive movements, or other reasonable suspicion of criminal activity. And there's also demographic information about the person who was stopped. Their sex, their race, age, height, weight, etc. There's also 10 so-called secondary circumstances or factors that led to the stop. These could be things like whether there was a report from a victim or a witness, sights and sounds of criminal activity, for example, bloodstains, ringing alarms, and other as well. And importantly, we know the outcome of whether or not a weapon was found. So you can see, was a weapon found, yes or no? If yes, was it a pistol or a revolver, a rifle or a shotgun, an assault weapon, a knife or a cutting instrument, machine gun, other could mean nunchucks, for example, if they're illegal in New York. And this is sort of amusing, but I think in the data there's actually at least one stop where apparently all of these different things were recovered. So I feel like that was probably a good stop. Maybe that's sort of uncontroversially a good stop. So anecdotally, there are all kinds of issues with this data. So there's anecdotal evidence that this data may under-include stops because officers just decide not to fill out a form, let's say, and it may also be over-inclusive stops if officers are pressured to fill out forms to meet quotas. And that's a real issue. Additionally, these forms are filled out by hand by officers after the stop, so there's worry about accuracy, both in how officers interpret how they should fill these forms out, but also even just transcription errors. So despite this, yeah.
Maybe it passed by already, but is there on the form an opportunity to ask the filler out of a form what questions they ask these people?
Oh.
Stop question in Frisk.
That's right. So so this is the full form. I think there may be room somewhere. So yeah, there's some room. There's some places where there's free text, but in general, this is it. What's recorded on this form is what's accessible in the data, minus any information that has to do with the officer.
How effective the question piece of it is.
Yeah, it's a good question. Unfortunately, detailed information about the questions officers ask isn't recorded on the form. There's this move in policing across the U.S., in fact, to have body cameras, and so one could imagine that in the future, if one were to get access to that kind of information, you could analyze what kinds of questions officers are asking for detail. There's actually an interesting study, not to get too far afield, but there's an interesting study by some researchers out of Stanford where they looked at body camera videos to determine, or body camera audio to determine whether or not officers in Oakland were interacting equally respectfully with drivers of different races. So that's an example of how new technology could be used. Yeah.
When people say this algorithm means the average, you're a statistician. So when I hear average, I think distribution.
Mm-hmm.
So is there any data that shows how well, say, the top decile in terms of predictors, whatever benchmarking does?
We're gonna get to that. Yeah, good question.
And also, I'm not sure, maybe I missed it, but related to that, is the arresting officer or whatever on these forms? So
it's on the form, but we don't have access to that data. Yeah, unfortunately. We would like to have officer information, but it's not available in the public data.
So how you can't really find out who's doing better than others?
That's right, not in the public data.
Oh.
Yeah.
Oh, but do you have access to that through information?
No. And even the saga of this public data is actually quite interesting.
I'm just interested in the data and the information. I want a better algorithm so people are judging better.
Yeah, no, absolutely.
Then you want to talk to them and find out what is it that you're doing.
Mm-hmm.
You're not even looking at that.
No, it's true, and I think this question actually highlights the difficulty of doing work in this area, because often the data that you would really like to look at is just not it's not feasible to get. So.
How are you going to do that? I don't relate with it.
Sure. So on other projects, so maybe just to give you an anecdote which will illustrate how hard it is to get this kind of data. When I first started looking at stop and frisk with my collaborators, what we really wanted to do was look at, for example, how the race of an officer compared to the race of the people who were stopped, and what sort of relationships were there. And so I called somebody at the New York Civil Liberties Union who was responsible for getting this data released publicly in the first place. I told her what I wanted, and she just started laughing, and she's like, good luck. I hope you're ready to file a lawsuit and sort of take the NYPD to court. So. There are just these sort of challenges that are hard to deal with as a researcher, but I hope that we're moving towards sort of greater transparency, and there's a lot of move to make data open, including policing data, and maybe at some point we will get to a point where the kind of data that you're asking about is public.
Are the people that are doing much better than one else?
Yeah, so we'll see at least how some algorithms do. Yeah.
Why didn't she want to say?
So they actually filed a suit earlier, which is why why this information is public at all.
But why didn't she sue about the arresting officer or whatever? He identified somehow.
So again, it's a good question, but I don't know. Yeah. So maybe let's table that question for afterwards, and let's move along. But it's a good question. I would love to have access to the officer information. Okay, so the one thing I wanted to say about the data is that in light of litigation, not just this 2013 case, but also earlier cases, the NYPD has made efforts to try and ensure the accuracy of the data that's collected. So there's, for example, supervisor review of these forms. And also this data has been used in previous academic work and in court cases. So acknowledging its limitations, we feel like there's still utility in examining the data. Okay, so what do? So first, we're going to use a logistic regression model to estimate the ex-ante probability that a stop would recover a weapon, and will include basically all the information that's available to an officer that's recorded on that form, but that's available to an officer at the time the stop is made. So this is things like the precinct, the type of location, demographic information, circumstances of the stop, etc. We fit it with all interactions, so there's something like 7,000 features, and we train it on years 2009 to 2010 and make predictions for years 2011 to 2012. So all the results that I'll show you in the following slides will be based on out of sample. And this is going to provide a performance benchmark, right? This talk is about simple rules, and a logistic regression model with 7,000 features is far from simple, but it's going to give us an idea of how well we could do if we use something much more complicated. So what we have with this model is we have a probability associated to each stop that was made that the stop would recover a weapon. Okay? So how do we turn these probabilities into rules for making stops? Well, what you could do is the following. You could say, suppose you're given some threshold, t, between 0 and 1. Then an officer makes a stop if the following two things hold. First, if the individual would have been stopped under the usual practice. And secondly, if the model estimated probability of weapon recovery is above that threshold. So you could think about this as a two-step procedure where officers first rely on their intuition and experience to decide whom to stop, and then they check whether or not the probability of recovering a weapon is above this specified citywide threshold, or specified threshold. And that first criterion is important because our model is only trained on stops that actually occur. So it may not generalize to the larger universe of people who weren't stopped. So given a stop rule, what we could do is we could rank stops by decreasing probability of weapon recovery, right? So we could just take all of our stops and reorder them. So the ones which have, say, a 99.9% chance of recovering a weapon at the top, all the way down to the stops that have like 0.001% chance of recovering a weapon. And we can estimate if only the best 1% of stops were made, or only the best 5% or 10% of stops were made, as judged by our model, how many weapons would have been recovered. And let's see. So this plot shows the performance of this logistic regression model with 7,000 features. So the x-axis is showing the percentage of stops ordered from most likely to recover a weapon to least likely to recover a weapon. And it's on a log scale. The y-axis shows what percentage of all the weapons in these stops would have been recovered if one were to just make, say, the best 1% of stops, or the best 3% of stops. And what we can see, the punchline of this slide, is that just the best 6% of stops would suffice to recover half the weapons. And in fact, the best, I think, 60% of stops, roughly, would suffice to recover 90% of the weapons. So the upshot here is that a small number of well-chosen stops would be sufficient to recover the majority of the weapons. Another point I should highlight is that of all these stops made between 2011 and 2012, something like 61% of the individuals who were stopped were Black. But if you just look at the top 10% of stops, say, only 44% of those individuals would be Black. So using this kind of model to make better stops, one could simultaneously make fewer stops, recover the majority of the weapons, and perhaps have greater racial balance in who was stopped. Okay, but this is supposed to be a talk about simple rules. So how can we make a simpler procedure for deciding which stops to make and which stops not to make? You could say it's impractical to imagine an officer in the field putting all this data into some big model and then getting a number and deciding what they should do. So what we'd like to do is reduce the number of features that we consider and simplify how we combine those features. And so to do that, we're gonna do a 3-step procedure, which I'll talk about in a little more detail in the subsequent slides, where first we just select a subset of features. And here, we're really only gonna select 3 types of features. First, those, you remember there were 10 primary stop circumstances on that form and 10 additional stop circumstances. So we'll take those 20 features, but we'll just forget about the 2 that were other. So we have 18 non-other stop circumstances. And then we keep track of which precinct the stop occurred in. There's 77 precincts, and whether the stop occurred in public housing, in public transit, or on the street. So we select a subset of features. Then we fit a constrained regression, a constrained logistic regression on these features. And then we just take the coefficients from this regression and round them to be integers. And if we do that, what we get is a 3-item stop rule. Does the suspect have a suspicious object? If so, they get a score of 3. Does the suspect, are there sights and sounds of criminal activity? A score of 1. Is there a suspicious bulge? A score of 1. So this is super simple. Just 3 items combined with small positive integer rates. So in a little more detail, the modeling step is as follows. So we're going to fit a constrained logistic regression, I'll call this the reduced model, on just the stop reasons, the precinct, and the location type. So here, there's these 18 non-other stop circumstances. There's indicator variables for the 77 precincts, and there's 3 indicator variables for the location type, whether or not the stop occurred on the street, on public transit, or in public housing. And on the left-hand side, we're trying to estimate the probability that a weapon will be recovered. And we impose this constraint that the coefficients on the stop circumstances are required to be non-negative. And that's to capture this sort of intuitively reasonable idea that all things equal, the presence of those stop circumstances should only increase the likelihood that somebody has a weapon. Now that being said, we also tried it without this constraint, and there were in fact some negative coefficients, but the performance was basically identical, so we prioritized simplicity and interpretability and kept that positivity constraint. So this is the first step of simplification. Okay? The second thing is we observe that we don't actually need probabilities. We just need scores that are monotonically related to probabilities. So we can forget about the logistic transformation. So we forget about the logistic transformation, and then we'll take those coefficients on the 18 stop circumstances, and we'll just round them to the integers. So whereas before there were 18 alpha j's, now we replace them with just 3 alpha j twiddles, which are integers. That's that 1 and 1 and 3 in that checklist that I showed you 2 slides ago. So you get this score, and then how do you use this score to make stops? Well, just like before, you say, you make a stop if you would have suspected that individual anyway, and if the score, SI, for the ith stop exceeds some citywide stop threshold T. Okay? So the thing I'd like to point out here is that SI being bigger than or equal to T is the same as the integer part being bigger than or equal to the citywide threshold minus terms that only have to do with location. Okay? So in practice, an officer would just have to check if the sum of 3 small integers is greater than some threshold, which varies by precinct and by location type. Now, you might say, well, is that really reasonable? What if officers moved around the city a lot? Then they would have to know a different threshold in every precinct and a different threshold in every location type. But in fact, the way that officers are usually deployed in New York City is they may end up spending long periods of time in the same precinct and the same location type. So somebody might be a transit cop in the 73rd precinct for long periods of time. So in practice, they just have to remember one location-specific threshold. Now this location-specific threshold, as written, isn't an integer. But if I'm checking whether or not some integer is greater than it, I can just replace it by its ceiling. So I can think of everything here as integers. So let's see what happens. So just for reference, this is the same performance plot that I showed you a few slides ago of our more complicated model. It'll serve as a benchmark. And here's what happens if we use our simple 3-item checklist with location-specific thresholds. So each circle here represents a different choice of citywide threshold. And what we can see, the punchline of this slide, is that the circles are very close to the solid line. That whereas 6% of stops suffice to recover 50% of the weapons using a logistic regression model with 7,000 features and all interactions, this simple 3-item checklist with locations that, with thresholds that vary by precinct and location type, you only need to make 8% of stops to recover 50% of the weapons. Yeah.
The 30% of stops captures the 75% of weapons, right?
That's right. In the stops that were actually made.
Yeah, so did you
Yeah.
actually look at how much more you would need to, how many more variables you would need? Because 50% seems like a low threshold.
Mhm.
This might be kind of more of a theoretical extent, but on a practical level, if you wanted the 75% of the
Mhm.
weapons, and if it's 30% of the stops, are there one or two more variables that you could add to drive?
So that's a good question. So you're saying fix a certain percentage of stops that you want to make. How much more complicated would you need to make this rule in order to get a higher percentage of weapons? It's a great question. I mean, the thing that I would suggest is that actually there's a bound to how much better you can do, even if you threw in all the features, because we know that the kind of fancy model, which has access to everything, can only do slightly better. So the point that I think your question really highlights, though, is that where you want to be on this curve is not a technical question, right? It's a policy question. It's something that ideally the community or the police department or politicians would get together and they would say, hey, we want to cut stop and frisk by 70%. Can you do this while recovering, 50% of the stops? And one would look at this and say yes, from this picture, we think we can. So yeah.
No, I'm just curious to make it less opaque. It's a very simple rule at the time. Also make it relatively easy to cheat.
Yeah. So that's a great point. And so, I would say there's two answers to that point, right? So the first is that in practice, you would imagine that you'd have to update this periodically to account for the fact that officers might game this. The second thing to highlight, though, sorry.
Not obviously.
Of the individuals, right? So I mean, you could ask the same question for the officers, right? That let's say officers have some incentive to make different stops, but even for the individuals, the thing I want to highlight is that there's sort of no magic in these three circumstances, right? To the extent that these map to real world actions, it's sort of like somebody has a gun in their hand, or if you hear gunshots, or if the bulge is a little weird. But I feel like the simplicity of this makes it hard to game. But it's a real issue that if this is publicized everywhere, then maybe people would stop carrying weapons in suspicious ways. But it's hard to know how this would happen in
I'm
practice.
more curious if people ask you about it.
Sorry.
I'm more curious if people you talk about police.
So actually nobody in law enforcement that I've presented this to has asked about this. In most talks, somebody raises this question. But actually, yeah, nobody in law enforcement. So again, I mean, I feel like we have time for one more anecdote. I presented this to a lieutenant, I think, at NYPD, and he told me something super surprising, which is that you may wonder how these UF-250 forms get turned into this electronic data set, which is publicly released, and apparently they're just shipped in boxes to some third-party company which transcribes them by hand, which I found super interesting. And so he seemed to think that there were lots of transcription errors as well. But that's a point which I wouldn't have known unless I had talked to somebody in the force. Okay, so here's where we were. I'd just like to quickly mention that this same framework for looking at the ex-ante likelihood that a stop will be successful in terms of weapon recovery can be used to examine constitutional violations. My collaborators and I also wrote a law review paper where we tried to examine how the legal system would need to adapt to accommodate the use of these statistical models. Okay, so let's change gears now. And if there are more questions on stop and frisk, maybe we'll hold them until the end. And let's look at an application of this simple rule method to a different part of the criminal justice system, namely the court system. So in the US, shortly after arrest, individuals are arraigned in court, which is where a prosecutor presents them with a written list of the charges against them. And at arraignment, judges have to make a decision. They have to decide which defendants who are awaiting trial are to be released on their own recognizance, I'll abbreviate that to be ROR, or which are subject to monetary bail. Okay, which defendants have to post collateral or have collateral posted on their behalf in order to secure their release before trial. So in practice, defendants often can't afford to post even moderate amounts of bail and end up going to jail awaiting their trial. And also, defendants may end up going to bail bondsmen and paying hefty fees in order to post their bail. So judges, on the other hand, are legally obligated to make sure, to try and ensure the defendant appears at trial. So these pretrial detention decisions have to balance the burden of bail on the defendant with the risk that he or she fails to appear for trial. So two things to note here. So first, there are other conditions of bail besides just being released or money bail. There's, for example, electronic monitoring. But in the jurisdiction that we focus on, whether a defendant is ROR'd or has money bail set are by far the most common outcomes. And secondly, in many jurisdictions, judges are also obligated to consider the public safety risk that if a defendant is released before trial, what's the likelihood that they're going to commit a new crime before their trial? But in the jurisdiction that we consider, judges are legally obligated to only consider flight risk. So what we look at is 165,000 adult cases involving nonviolent offenses charged by a large urban prosecutor's office. Not sure if I'm supposed to say which, but you may be very familiar with it, and arraigned in criminal court between 2010 and 2015. So importantly, we exclude cases here in which a plea deal was taken, because if a plea deal was taken, there's not going to be a trial in the future. So there's no chance that a defendant could fail to show up for that trial. So we have 64 features of each case. We have 49 features that are related to the charge, whether it was theft related or gun related, for example, and 15 features that capture circumstances of the defendant, their previous arrest record, their previous conviction record, their age, their sex. So in this data, 69% of defendants are ROR'd, of which 15% fail to appear. Now, of the remaining 31% who have bail set, 9% of them fail to appear. So you might say, okay, how could somebody fail to appear if bail was set? Well, they could post bail and then skip their trial. And in fact, that's what bail is supposed to prevent. So the overall failure to appear rate here is 13%. And I should mention this is also joint work with a set of collaborators. So our goal, just like in the stop and frisk case, is to create simple rules to improve these detention decisions. And we want to benchmark these simple rules, again, against more complicated statistical models, just like we compared our simple 3-item checklist in the stop and frisk case to this logistic regression model with lots of features. So we need to do two things. We need to construct these rules, and we need to evaluate them. Okay? Now, I'm just going to mention right here, and I'm going to come back to this, that the evaluation part is hard because it involves a counterfactual estimation problem. So I'm going to come back to that. So what we do to construct these rules is we divide our data into 3 chunks or 3 folds. And then to construct this simple rule, we're going to just look at the first fold of data. Okay? We'll restrict to those cases where a defendant was in fact released or ROR. And we'll do the same 3-step procedure. We'll select a subset of features. And here we're just going to select 2 features. We'll select age, and we'll select the previous number of failures to appear. So just 2 features. We'll fit a regression, a logistic regression on these features, where we predict whether or not the defendant fails to appear. And we'll just rescale and round the coefficients to be small integers. And this is what we get. We get a essentially 2-feature checklist, 2-item checklist, where you get a score depending on what age you're in, what age bucket you're in, and you get a score depending on how many times in the past you failed to appear for trial. So for example, you could say, I'm going to, if faced with a new defendant, I'm going to use this rule to compute their score, and I'm going to ROR them if and only if their score is below some threshold. So I might set a threshold of, let's say, 3.5, and maybe somebody comes in who's a 23-year-old with 1 previous FTA, and I would say, okay, they're 23, so they get a score of 2. They have 1 previous FTA, so they get a score of 2. Their score is 4. That's higher than my threshold of 3.5, so I would have the judge set bail. The other thing I wanted to mention, I forgot, is that these features aren't surprising, right? It's sort of well known that age correlates with failure to appear. and that history of failing to appear correlates with failure to appear. Yeah.
I'm surprised at the seriousness of the charges.
It is surprising, yeah. And we tried this with sort of many different strategies to select subsets of features, including some algorithmic strategies, and the seriousness of the charge never appeared. I think in one version, so we in the paper where this appears, we formalized this strategy. So rather than an ad hoc method of selecting features, we select them with forward stepwise regression. And if you do that, I think you get, I think if the charge is DUI related, then people actually have a negative score. So they're sort of more likely to show up for trial. But surprisingly, the seriousness of the charge didn't appear. But the other thing to highlight is these are all nonviolent offenses. So there's a limit to, let's say, how serious they can be. Yeah.
So for setting the score on the ages,
Uh-huh.
did you programmatically run models and set various different cut points and have it automatically come up with cut points that you the best results, and then make it simpler, like with these ranges, or how did you?
So basically what we did was we selected age and prior number of FTAs just using intuition, and then we fit this logistic regression, and then just rounded the coefficients. So we rescaled them to be in the range -3 to 3. So we divided by the magnitude of the largest coefficient, multiplied by 3, and then we got these scores. So there's very little. I mean, the thing I want to emphasize here is that in both this method and in the previous method, there's basically no optimization going on. So we're not trying to find the best rules. We're trying to find the sort of simplest thing. So there's other work, especially coming out of the ML world, which sort of uses, let's say, mixed integer programming to come up with simple interpretable checklists like this. And I would say that the benefit or the unique aspect of our strategy is that it's super simple. It's sort of much more reasonable, I would argue, to have a practitioner fit a logistic regression model and round some coefficients than to solve a mixed integer program or set up a mixed integer program. Yeah.
It begs the question, how much better?
So I have that in an appendix slide, and maybe in the Q&A I'll show you. The upshot is they are no better.
What's that?
They're no better.
Oh, thank you.
Yeah. Yeah.
You said you use this feature because that's usually what.
Yeah. So it's a good question.
The question, I think they cannot.
Oh yeah, sure. So the question, I guess, for those of you who aren't here in the room is feature selection is the hard part, right? So how come you necessarily selected these two features? So again, in the paper we have this algorithmic method of selecting features, and when we select those features, we have a larger set of features, and that larger set of features includes age and previous numbers of failures to appear. So the way we like to think about it is there's some combination of human intuition and expertise and algorithmic selection. So if you were to do a forward stepwise regression where you say, I just want to keep 10 features, you would find that age and previous number of failures to appear are among them. And then you might say, okay, well, I've been doing this a long time, and I think probably age and previous number of failures to appear capture, capture somebody's risk of failing to appear enough. So I'm going to further restrict that set using my own intuition, and I get these two. So this wasn't selected by some procedure where we, let's say, tried every subset of 2 features until we found the ones that were optimal. Yeah.
Could age have a compounder in the sense that?
It's true. So there's a sort of a large body of work, I guess, which sort of explains perhaps why age is related to your likelihood of failing to appear or not. Intuitively, there's this idea that people age out of crime. And that's, to the extent that crime is the right word to use to talk about failing to appear for trial, our idea is that that's what's going on. Okay, so let's see how this rule does, right? It's pretty simple. So to benchmark performance, we also construct complex rules on the first fold of data. And here we'll compare to a random forest classifier and to an L1 regularized logistic regression model, a lasso model. And we'll allow these two complex machine learning models to estimate failure to appear using all 64 charge and defendant features. So this is a tough task for the simple rule, right? It only has 2 things, whereas random forest and L1 and the lasso have 64 features. Okay, so let's go back to this question of evaluation, right? I mentioned this was the tricky part. So given a rule, in practice, we really want to know two things, right? We want to know what's the proportion of defendants that would be released under that rule. Status quo is 69% under what judges are currently doing. And secondly, we want to know the proportion of defendants who subsequently fail to appear at trial, who would subsequently fail to appear at trial. So what you would do in theory is you'd just take this rule and you'd actually apply it to real cases and you'd see what happens. But what we'd like to do is we'd like to forecast the second and the first on historical data, on data that we already have. So given a rule, given a checklist, it's easy to estimate the first quantity. You just apply the rule to your data and you see how many defendants it would recommend ROR and how many defendants it would recommend release. But the second quantity is tricky. And the reason why it's tricky is because for each defendant, we only observe what happened conditional on the action the judge actually took. So for example, if bail were set for somebody and they showed up for trial, and our rule recommends that that person should be released, well, we don't actually know what would happen if they were released because we didn't observe that outcome. So you can contrast this with the stop and frisk case, where in the stop and frisk case, there's people who could be possibly stopped. An officer makes a decision to stop somebody or not to stop somebody, but the officer's decision to stop somebody doesn't change the immediate chance that they're carrying a weapon. Whereas in the pretrial detention setting, you have people who are arraigned. A judge makes a decision, do I set bail or do I ROR that individual? You observe an outcome conditional on the action the judge took, but you don't know what would have happened if the judge had done the other action. So that's why this is tricky. So our strategy here is to use so-called response surface model. And the idea is we just fit a model to predict the counterfactual outcome. So we train a lasso model on the second fold of data, where we include the judge's action as a predictor, and we apply this model to estimate for each defendant the probability that they would fail to appear if they were ROR, and the probability that they would fail to appear if bail were set. And I should mention that we tried two other standard approaches in the causal inference world, inverse propensity score weighting and doubly robust estimation, and we got qualitatively similar results. So given these response surface models, how could you actually use them in combination with this simple checklist to estimate the counterfactual outcome? So here's a sort of a chart which shows what our estimation strategy is. So suppose you have 5 cases here. So imagine that each row in this contrived table represents some case. So we know what action the judge actually took. That's the observed action. So maybe for the first defendant, the judge actually ROR'd that person. And then in the third column, we know what actually happened. We know that that first defendant, the judge ROR'd them, and they showed up for trial. The second defendant, we know that the judge set bail. We know that they failed to appear for trial, etc. And the first column represents the action that our rule would recommend. Okay? So what we do is when our proposed action, when the recommendation of the rule agrees with the observed action, we just use the observed outcome. But when the proposed action disagrees with the observed action, what the judge actually did, we use our model. So for example, in the third row here, the judge actually ROR'd the defendant, but our rule recommends that we set bail for the defendant. So instead of using the observed outcome, we use our model estimate, our response surface model estimate of the probability that that defendant would fail to appear if bail were set. So this approach assumes that the judge's action is ignorable given the observed covariates. Another way of saying this is that conditioning on observed covariates, those who are ROR'd are similar from the point of view of potential outcomes to those who aren't. Or another way of saying this is there's no unobserved confounding. This is a strong assumption. And we'll come back to this assumption after I show you the results. Yeah?
Unlike the stop and frisk in this case, I assume you know which judge.
Yes, we have Judge.
So you can don't you have like distribution for the top decile versus the bottom decile?
So I'll show you how judges vary. Yeah.
Okay,
Another thing I should mention quickly is, and I would have said this later, but it's important to mention, is that judges in practice see a similar distribution of defendants, but cases are not perfectly randomly assigned to judges. Okay. Yeah.
I know what you're saying, but so that if you're doing that, you're essentially simplifying the thought that you extrapolate the features which are the one the model decided to use. So it's a little less surprising than a simple modeling that approach that.
Yeah, so I guess the extent to which you find this surprising sort of depends on your framework, right? I would imagine if you're a judge, you might find this more surprising than if you're a statistician, let's say. At least to me, it was surprising, I guess. So I mean, there's two aspects here that are surprising, right? One is, or potentially surprising. One is the performance of our model, which I'll show on the next slides, relative to human decision makers. And the second is the performance relative to a random forest in a lasso. So one may find one or both of those more surprising. Okay, so in the interest of time, I'm gonna maybe go through the rest of the slides and then I'll put questions until the end. I think we have a Q&A session. Yeah. Let's see, so things are moving here, but they don't seem to be moving on the screen.
It's moving here too.
Oh, no.
Oh, there we go. Okay, so I don't know what happened, but I'm gonna show you in a series of plots the performance of these various models. So here, the x-axis shows the proportion of defendants that are released on their own recognizance, or ROR, and the y-axis shows the estimated proportion that fail to appear, and the black dot here shows the status quo. So right now, judges ROR 69% of defendants, and they have an overall failure to appear rate of 13%. So you really want to be somewhere here, right, in the lower right quadrant, where you're simultaneously releasing more defendants and having a lower failure to appear rate. That's intuitively maybe what we would say a good rule is relative to the status quo. So here, each of these lines shows a family of policies, a family of rules that you would get from each of our two complicated models, random forest and lasso, based on setting different thresholds. And what you can see, the punchline of this slide, is that there are statistically informed strategies that simultaneously release more defendants and have a lower estimated failure to appear rate. So each of these red dots shows the performance of our simple 2-item checklist with a different choice of threshold. And importantly, that rule that I mentioned, that I said, you know, when I showed the checklist, and I said, if there is a threshold of 3.5, that represents the red dot right there. I guess right there. Which would release 79% of defendants and have roughly the same estimated 13% failure to appear. So it would detain something like 1/3 fewer defendants. So the surprising thing here is how close those red dots lie to the black and the gray line. Here, each of these circles represents an individual judge with the size of the circle scaled by the number of cases that judge saw. And all of these circles are more than 1,000 cases. So what you can see is that although judges see similar distributions of defendants, they vary pretty dramatically in the proportions that they release. Some judges are releasing 50% of defendants, some judges are releasing close to 90% of defendants. And the second thing to highlight is that for almost every judge, there's some statistically informed strategy which outperforms that judge in the sense of releasing more defendants while having a lower estimated FTA rate. Yeah.
Maybe I'm reading this wrong, but is there a way to split this out?
So I guess, I'm not sure if I have that plot here, but yeah, maybe we can talk about it more.
I'm always curious about what the better, in my field, it's use distribution in terms of outcome.
Yeah.
What we saw moving money ball.
Yeah, it's a little tricky, right? Because I'm sort of, you know, on the one hand, I'm kind of saying, well, judges see a similar distribution of defendants, but on the other hand, I'm a little reluctant to say that cases are perfectly randomly assigned to judges because they're not. So I think we can't read too much into, you know, if judges actually saw exactly similar distributions of defendants, then we would say, oh, let's just look at their FTA rate, but they don't. So it's hard to directly compare judges. Okay, so why might judges not be doing as well as these simple models? So this grid aims to give some intuition as to why that might be the case. So what I've done here is I've taken all of the cases and I've binned them by their previous number of FTAs and their age. Okay? Now the number and the shading, which reflects the number, represents how many defendants in each bucket, in each box, are currently ROR by judges. So for example, judges currently ROR 33% of defendants who are 51 or older and who have 2 or more previous failures to appear. Now, our simple rule with a threshold of 3.5 would release everybody to the left, below and to the left of the thick black line, and would set bail for everybody up and to the right of the thick black line. But what we can see is that aside from defendants who have 0 previous failures to appear, the risk of failing to appear doesn't seem to be too correlated with the judge's action. So for example, what we would say are low-risk defendants who are 51 plus with 1 previous failure to appear are ROR at basically the same rate as what we would say are high-risk defendants who are 18 to 20 years old with 2 or more previous failures to appear.
Sorry to clarify.
Sure.
You interpret that as a positive thing or negative thing?
I interpret it as a negative thing, I would say. So, I mean, I'm making certain assumptions here, right? I'm making the assumption that judges really are only optimizing for this one characteristic. But I would say that, besides the fact that judges, for whatever reason, are RORing these relatively high-risk defendants as opposed to these relatively low-risk defendants, there's also issues of inconsistency, right? So judges, a judge may see 2 different defendants who look at least identical in the data, but some judges may release one, other judges may set bail for one, whereas our algorithm is going to do the same, going to make the same recommendation for every person.
That's just because you said they're the same.
Sure. Yeah, it's true. It's true. No, I mean, it's fair. And so, I'll also kind of reference this sort of, this work out of psych and business literature, which says that essentially in a large set of circumstances, kind of almost trivially simple statistical models outperform judges and doctors and experts who have been making these kinds of decisions for ages. So again, maybe it's not too surprising, but the assumption that I'm gonna highlight in the next few slides, and the one which I think is really perhaps the place where one can ask how plausible any of this is the ignorability assumption. How well does our data actually capture the circumstances of a defendant? Because it's very plausible to imagine that judges see things that we don't see, right? So let's examine that a little more. So here's the question, right? What if judges in fact base decisions on information that isn't recorded in the data? It's a real worry, right? Our estimation strategy relies on this essentially not matter. So I'll kind of address this question in 2 separate ways. So the first is that although judges see similar distributions of defendants, they differ in the proportion that they release. So if we examine judges who mostly act in the same way as our simple rule, we find that we still estimate failure to appear at about 12 to 14%. So here's a plot where we take those judges that I showed you in the previous slide, and what we do is we apply our response surface modeling estimation strategy to each of the sets of cases that a judge sees separately. And that gives us the y-axis value for each of these. So this is saying that for these cases, which one judge saw, we use our response surface estimation strategy just on these cases, and we estimate in these cases a failure to appear rate of something like 10.5%. And on the x-axis is the proportion of judge decisions that agree with our proposed policy. So we might expect that if we examine judges who systematically agree more with our proposed rule or less with our proposed rule, if we saw systematic patterns in our failure to appear estimate, we might say that there's some unobserved heterogeneity going on, right? Maybe another more intuitive way to say this is, suppose we had a judge who agreed with our policy 100% of the time. And suppose that cases were randomly assigned to judges, then it would be very easy to evaluate our rule. We just see what the outcomes were for that one judge. So instead of that, we have judges who mostly agree with our proposed policy. and we have cases that are not perfectly randomly assigned, but are somewhat randomly assigned, and we still find consistent estimates. So the second strategy is an adaptation of this method developed by Rosenbaum and Rubin in the 80s to assess the sensitivity of our estimate of failure to appear to unobserved confounding. So the idea here is we assume that there's some unobserved binary covariate U, so something in the data that we didn't see, and we assume that the judge's decision is ignorable given the observed covariates and U. So you could think about U being something maybe like whether or not a defendant is a single parent. So this is something that we don't see in our data, but let's say a judge does see this. Now, being a single parent could affect the probability that somebody is ROR or sets bail. Maybe a judge is more likely to ROR a defendant who's a single parent. And being a single parent could also affect the likelihood that somebody fails to appear given ROR or given bail. So the idea behind this strategy is if you specify 4 parameters, the prevalence of this unobserved binary covariate, the prevalence of single parentness, let's say, the effect that the unobserved binary covariate has on the judge's decision, the effect that the unobserved binary covariate has on the probability of FTA given ROR, and the effect that the unobserved binary covariate has on the probability of FTA given bail, then the Rosenbaum-Rubin framework allows you to see how sensitive your effects of, your estimates of effects are to these different choices of parameters. And what we find is, similar issue. Maybe I just wait for a second. Oops.
I think that's because of the Wi-Fi.
Okay. The upshot is things don't change too much. You search over a pretty reasonable range of parameters for these U. I think that was my second, no, maybe one of my last slides. So, worst case, just take my word for it, or you can look at it. But hopefully, there's a few more slides. So hopefully,
And you prove that this sensitivity is more for the simple.
yes. So for the simple rule and for the complex rules. So in the plot, I'll show you sensitivity estimates for both the simple rule and the complex rules. Yeah. So the Rosenbaum-Rubin framework, as written, is for sensitivity of an average treatment effect, but we adapted it to this policy evaluation setting, where instead of estimating an average treatment effect, we want to estimate what would happen if this new policy were put into this. So some people are treated and other people aren't based on their covariance.
So, since you're trying to oh, there you go. Well, I was just going to say that this makes me wonder, and I doubt there's an answer to this, but it just seems to me that there are things we can't know about what the judge sees, and I would think some of those things, unlike maybe in other disciplines or something, some of those things would be really important in their decision making. But what strikes me is that these simple rules, that if judges have this in mind, these rules in mind to be part of their decision-making process. I'm just curious how things might change.
So that's a great question, and I sort of feel like, at least to my knowledge, it's essentially an open question. So the broader question perhaps is, how do human decision makers act if given algorithmic recommendations, transparent or non-transparent? And you know, it's not clear, I would say. So you know, there is some sort of ethnographic or anecdotal evidence that that decision makers sort of behave in perhaps unexpected ways. They don't follow the rules as often as one might expect. You could imagine, in fact, a judge using a rule like this and making strictly harsher decisions, right? You could say, you know, I'm a judge, and as long as the rule agrees with what I was going to do anyway, I follow the rule. But let's say the rule recommends setting bail, and I would have ROR'd, I follow the rule. Let's say the rule recommends RORing, and I would have set bail, I override the rule. So it's, at least to my knowledge, it's pretty unclear. But I'm very curious about it, both in this setting and in other settings. Yeah.
Well, in the way of calling a person a judge, if it were possible to apply the simple rules, they would no longer have to be a judge, they would be the administrator,
Mm-hmm.
you know? But the value of this is to shrink the significant outliers from, being in the, in line, so to speak, with the other judges.
Mm-hmm. I mean, the other thing to mention, right, is that at least in the legal system, it's hard to imagine judges being completely out of the loop for making these kinds of decisions. I feel like it would probably violate due process. So the idea is that there is going to be this human who can make this decision to override or not to override. But without rolling it out, I'm not sure how judges would actually react. And this is the kind of thing where you could imagine that maybe how they react would also depend on the format that the information is provided to them in. But to my knowledge, and again, maybe I'm just not sure. I haven't seen many or any like large-scale empirical studies of how human decision-making in these kinds of contexts is affected by having access to algorithmic recommendations. So I'll just wrap up. In the interest of time, I'll just sort of read what's here, which is that these ethical and legal and practical constraints inform a technical approach that emphasizes simplicity and transparency. And I'll just again say that in our paper, we describe this method in more generality, and we apply it to 22 standard ML data sets, and we show that in general, it performs comparably to things like random forest and lasso and logistic regression. And I have two more slides which talk briefly about other projects that I'm working on. And because this is a data for social good seminar, I thought that maybe it would be interesting to folks to hear about some other projects that are not about simple rules, but are still, I think, about using data in the service of social good. So I'll just quickly describe those before I wrap up. I work also with the New York City's Administration for Children's Services, and they are interested in using predictive techniques to better allocate resources to what they call first-time families. So these are children and families that have essentially no prior interaction with the child welfare system beyond the current investigation that they're involved in. And so the observation is that of these children, many of them are never going to have another interaction with the child services system. And some of them are going to keep coming back. And the question is, if you could determine who those children were, you could, on the one hand, provide beneficial services, allocate beneficial services to families who have high need, and on the other hand, you could avoid unnecessary services for families with low need. So again, you're using predictive techniques to summarize information in a way which allocates limited resources. So the second project I want to highlight is to use, this is in collaboration with some folks formerly NYPD, to estimate gunfire incidents in high crime areas of New York City using multiple data sources. So crime in general is very hard to measure because often people who are involved in it have a vested interest in it not being measured. But new technology, for example, there's a system called ShotSpotter, which are microphones deployed throughout parts of New York City, aim to address this by automatically detecting and localizing instances of gun discharge. And so our idea is, could we combine multiple different data sources? 911 calls about gunfire, so citizen-initiated measurements of gunfire, police pickups, so police records of gunfire, these ShotSpotter sensor alerts, databases of shootings and homicides, which might have information from, say, hospitals, and complaints by civilians, so incidents where there's a victim. Could we combine all of these using statistical methodology to come up with more accurate estimates of gunfire, volume of gunfire, and could we understand what attributes of a neighborhood, let's say, or of time and place are related to the prevalence of gunfire? So this is a work which is in progress. So my final slide, I'll just wrap up by saying, I was gonna wrap up by saying essentially the big open question here is how human actors use these algorithmic tools. So I'll just repeat that, and I'll say that a complete understanding of how these techniques are actually used and deployed is essential to making sure that they function as intended. And that's all I have. Thanks. Sure.
As well on theme.
Yeah, absolutely. Uh-huh.
It'd be interesting, maybe done this, see a study of what characters judges are not less.
So it's interesting. So
Could it be older or younger? Could it be more Republican status? Education? I'm just curious.
So in our data, we have a judge ID, but we have no other information on judges. Potentially, we could get it. We work in collaboration with somebody in that office, in the DA's office. But data like that, generally data on officers, data on judges is hard to get, particularly in the criminal justice setting, because there's a real culture, I would say, of being kind of closed about the information that's released, for reasons that may be totally reasonable or not.
But what about the identifier? Yeah.
So,
And I want to add on top of that. I think I might be wrong, I'm pretty sure my Judaism in Orthodox Judaism. The judges, I think they're required to have a family. At least in certain contexts.
Sorry, they're required to what?
To have a family.
Oh, really? Okay.
Males, the rabbis.
Huh, okay.
To have a family because they understand the world a little more. It's a little more complex. I think that's the thing. And I might be totally wrong.
That's really, so if that's true, that's really interesting. One of these,
I want to look this up.
Yeah.
It's been a while since I looked at this, but I always remember these kind of curious facts.
Yeah. No, that is super interesting. It actually reminds me of this study. There's this well-known study about judge decision-making in Israel, about how judge decision-making changes over time, and in particular in proximity to lunch breaks and to coffee breaks. It's an interesting study. It definitely has its critics. But one could imagine doing the same kind of analysis using our data. I mean, we know when an arraignment occurred throughout the day. We know characteristics of the defendant.
I was going to bring that up, and I believe it was like by Thursday afternoon, they were making, they were easier on the cases. And more interesting was that you would think that the judge might be favoring a decision for the person with their same ethnicity, but in fact, given that there was that laid back Thursday afternoon kind of thing, they were actually winging on a person who you would think they would be, heavier throwing the book at.
Yeah, it's super interesting. And one of the big criticisms of that study is just that the effect size seems implausible. It's like judges start the day, making favorable decisions something like 65% of the time, and then right before their coffee break, it's like 0% of the time. And so, one of the arguments is like, just there's no way we can believe this study because like if that were the case, then it would be chaos. But it's super interesting, and it is the kind of thing where one could imagine doing a kind of more in-depth analysis using this larger data set. I mean, they looked at 8 judges and something like 1,000 cases, and we have hundreds of thousands of cases.
And it made me wonder about that idea associated with the judges and what they were doing in the courtroom, perhaps with the police officers and the stop and frisk. What time do they start their shift? And, how do you happen to know how the police schedule goes, when their shift changes?